Well, hello again out there, my fellow Almontians. Today we're going to be chatting about the Earth's motions in space and some proofs of those motions. Specifically, of course, rotation and revolution. Because let's face it, standing on Earth, it just doesn't feel like it's moving at all, right? So anyway, we're going to address that today and, of course, delve a little deeper into astronomy as the days progress. I'm going to start out with a comical little clip from the Simpsons. I don't know if you guys ever watched The Simpsons. They're dumping stuff in the toilet bowl and then flushing it to see the direction of rotation. And of course, that relates to the Coriolis Effect, and we'll talk all about that. So check it out.
Go, toothpaste, go! Move your pasty white butt. Come on, shampoo, you can do it! Yay, I won your stupid bathroom products race! No fair. You only won because you had the inside track. If the water was spinning the other way...
It never spins the other way. In the northern hemisphere, water always drains counterclockwise. It's called the Coriolis Effect.
No way. Water doesn't obey your rules. It goes where it wants. Like me, babe.
Yes, Bart. Why don't you try it and see?
I know I've seen it go the other way.
All right, all counterclockwise in the northern hemisphere.
Toilet. You'll prove me right.
And there's counterclockwise again.
Oh, for Pete's sake, Mark, use the plunger.
The Simpsons. So yes, in the northern hemisphere, a freestanding drain, right? Not if you force the water the other way, but in a freestanding drain, it'll spin counterclockwise, and that's because of the Earth's rotation. We call that the Coriolis Effect, and that's the reason why wind and water, can't go in a straight line on the Earth's surface, right? Because the Earth is spinning beneath them, so they get curved. In the northern hemisphere, things curve to the right, the southern to the left. All right, so read through this blurb here. All about rotation. All right, and basically, of course, that's the spinning on an axis. And a lot of students confuse the terms rotation and revolution. They are not the same thing. You cannot use them synonymously. Okay, Earth's axis we know is tilted at 23.5 degrees. That gives us the seasons, gives us changing length of day and night. And of course, that's pointed to our North Star, Polaris. Okay, its rate of rotation is 15 degrees per hour. Right, it goes from west to east, and that's why New York is earlier than California, right? Because as it rotates, New York goes into night before California does. It has to catch up. Each time zone, of course, is 15 degrees because of that rate. And every time you cross another 15 degrees of longitude, you have to change, the time by an hour on your watch. Okay? Okay. There's an apparent motion and then there's a real motion. The apparent motion is what looks like is happening, right? The sun going across the sky, the moon going across the sky. But the real motion is what's actually happening. And of course, that is the Earth's rotation, right? It makes it look like the sun and the moon are going across the sky. Really, that's the Earth rotating. Okay, there are other motions involved, but that's the real motion for this. All right. What would happen if the Earth sped up to a rotation of 30 degrees per hour? Well, what do you think? Looks like it would go faster, which means the days would be, of course, shorter, right? Yeah, if we were spinning 30 degrees an hour, instead of having a 24-hour day, we would have a 12-hour day. And you can do the math on that, right? That's 360 degrees divided by how many degrees per hour, and it would tell you how long the day is. If the Earth slowed down, right, to 7 degrees per hour, well, obviously the days would get longer, right? Okay. Everybody always wants more. You hear a lot of people say, oh, there's not enough time in the day. Well, all you got to do is slow down the Earth's rotation. You got that problem solved. Okay. Let's keep going here. How do we prove Earth rotates? Because it certainly doesn't feel like it. There is some evidence, right, that Coriolis effect we just talked about, that curvature of wind and water on the Earth's surface. Another one is a neat experiment a gentleman put together in France. His name was Jean Foucault, and he put together this pendulum setup in the, I always mix up the name of this building, in the Pantheon, I believe, in Paris. I know there's one in ancient Greece as well, but I believe it's the Pantheon. Yeah. And he set up this experiment, and he invited everybody from the town to come in, and he wanted to show them that this free-swinging pendulum would not stay in this same straight path. It would curve, and he said that was due to the Earth's rotation. And certainly it did. It knocked down all these pins, and if it only went back and forth, it would have only knocked down 2 pins. So at the end of the day, it ended up going in a circle, and that was attributed to the Earth's rotation. Okay, so make sure you get that in your notes. Other evidence of rotation, maybe you've seen pictures of star trails. Because of our 15 degrees per hour, the stars will appear to move across the sky at 15 degrees per hour. And if you do that time-lapse photography trick we've been talking about, right, you hold the lens open, you get these pretty wild images right here. Check it out. They call them star trails. And depending upon what direction you face your camera, you'll get a different picture, right? So this is looking due north, and that's everything going around that center star there, Polaris. Looking west, you'll get that view. Looking east, you'll get this view. South, that view. But it's just like, I'm sure you've seen a picture of cars in traffic. You'll see like streaking taillights because the car is moving. Well, that's what's going on here. Streaking stars because the Earth is moving. All right, they call them star trails. If the Earth did not rotate, then you could hold the camera open all night long. That's the picture you would get. No evidence of motion. Okay? And then we get to revolution, which of course is a completely different motion, right? Now we're not talking about spinning on an axis. Now we're talking about literally a path around something else. In this case, the Earth around the sun. Make sure you read that. Okay? And there it is, the planet's moving around the sun, right? We also call it an orbit. And our orbit, of course, lasts 1 year, but not every planet has that orbit. Different planets are different distances from the sun, and therefore take different amounts of time to travel around it. Okay? There's our orbit, 365 days, roughly. It's actually 365 and about a quarter days. So every 4 years, as you know, you add up a quarter plus a quarter plus a quarter plus a quarter, you get a whole extra day. And that's when the calendar has a leap year, right? We add an extra day on February, so that year we'll have 29 days in February to make up for this extra quarter every year. Okay? The revolution also is the reason we have the whole Zodiac phenomena. And a lot of people get confused. They say, well, how come I can't see my sign during my birth month? Well, that's true. It's on the opposite side of the sun, right? And that's the whole idea where when you were born, your zodiac sign disappeared from the view of space. And the thought was that it became part of you, right? It makes you up. Well, really what was happening is, you know, here, let's say you're in May, during the day, right, you can't see behind the sun. It's too bright. But there you are. You're either a Taurus or a Gemini there. And when you rotate into night, you're seeing Virgo, Libra, Scorpio, Sagittarius, because these are in the nighttime. But once you go to daytime, your sign disappears. And those are all your zodiac signs. And they say it's under the you're under the influence of that sign because it disappeared from space at that time. Okay? All right, evidence of Earth's revolution. Well, we see different constellations throughout the year, right? If Earth didn't go around the sun, we would see the same constellations all the time. This apparent diameter, right? How big something appears. If I get real close, I appear bigger. If I get further away, I appear smaller. And of course, that changing distance to the sun has to do with the revolution. Because the revolution is not a perfect circle. So at some points you're closer to the sun, at some points you're farther away. These are the actual differences in sun measurements. You could see when you're further away, aphelion, if you remember that term, the sun appears smaller. And when you're closer, perihelion, you can see the sun appears just a little bit bigger. And that's called apparent diameter. Okay? Same thing with the moon. We use the terms apogee and perigee instead of the other two, but same type of thing. Look at the difference in size on that one, right? Because the moon's a lot closer to the Earth. So changing the distance to the moon makes a real big difference. The sun's already so far away that little change in distance isn't that noticeable. But that's pretty amazing right there. Okay? And of course, other evidence of revolution, seasons, right? You need the Earth's tilt, but also it needs to revolve around the sun. And when it does, we get seasonal change. And these are all evidence of Earth's motions. Okay? So review that. Make sure you get all your notes in there. There's some summary questions. Work hard on. All right? And we'll go through it all. Meet you back in the meet. See you there.